Hello, everyone. I'm Marina Jurica, and I'm coming to you live from NASA's Jet Propulsion Laboratory here in Southern California on a beautiful sunny day. We're here to talk about the mission SWOT, which stands for Surface Water Ocean Topography. And SWOT is going to be able to track over 90% of the water on the Earth's surface. And it's a joint mission between NASA and CNES, which is the French Space Agency. And we're going to break down some of the first data images that have come down from SWOT with JPL engineer Curtis Chen. He's going to be joining us in just a few minutes. Now, Curtis has been with the SWOT mission for about 8 years, and he's going to show us some of these exciting first images that have come down from the satellite. SWOT launched last December in great fashion at Vandenberg Space Force Base, and it's to do its science work. So if you're giving me just a few minutes here, I'm going to invite Curtis in from our at NASA Earth IG station. And hello, Curtis. How are you doing today?
Good. Hi, Marina.
So tell us a little bit about where you're joining us from.
Well, I'm here at the Earth Science Center at JPL, and I'm standing in front of a really big display that helps us visualize our fleet of Earth-observing satellites and some of the data they provide. So behind me right now, you can see an animation of the SWOT spacecraft orbiting over the Earth at about 900 kilometers altitude, or about 550 miles, giving us some exciting new data that we're going to talk about today.
Oh, thank you so much, Curtis. And it's a pretty cool scene behind you at NASA Eyes, and a lot of people can just pick this up at their home computer. So tell us a little bit about how everyone at home can see NASA Eyes and see where SWOT currently is in orbit.
Yeah. You may not have a big display like this at home, but if you go to eyes.nasa.gov, eyes is in your eyes, you can interactively look at where these satellites are. You can look at the data they provide and just get a nice cool visualization of all the great things that these satellites are doing for us.
And it's just not SWOT. You're going to be able to look at all of the satellites, which is pretty cool. So head over to NASA Eyes after this live stream. Now tell us a little bit, Curtis, about SWOT. And if you're just joining us, SWOT stands for Surface Water Ocean Topography. And we're here to look at the first data images that have come down in just a few minutes. But just to get us started, Curtis, what is SWOT?
Well, SWOT is a mission to study water on Earth and how it changes and how it moves around over time. So water is one of those things where it's really hard to overstate how important it is, right? Civilizations have risen and fallen around it. Wars have been fought over it. And it's a thing that makes our planet truly unique among all the planets that we know. So SWOT is going to help us understand this precious resource better by forming global high-resolution maps of water surface heights. And it'll give us a new map every 3 weeks so we can look for those changes. So these water heights are important because if you know how high the water is in a reservoir, you know how much water is in it. If you know the slope of a river, you can tell how much water is flowing along it. And over the oceans, the subtle variations in heights over the oceans can tell us a lot about the ocean currents and how eddies are forming and dissipating. Kind of like how if you stir a cup of coffee, the level of the liquid gets higher near the rim of your mug and it's lower in the middle. So by sensing the height variations over the ocean, even though they're really small, we can get a sense of how things are changing over time. So SWOT is going to provide a wealth of information for oceanographers and hydrologists around the world.
That's so exciting, and I'm sure everyone at home can't wait to see these images. So recently the satellite sent back that first taste, and we call it first light. And can you tell us a little bit about what first light is and why it's so important?
Yeah, first light is, for a mission like SWOT, it's the first data we get of the Earth from space. And it's an exciting milestone because we've got an international team of engineers and scientists who have been working really hard for many years designing and building and testing SWOT on Earth. So now SWOT's in space, it's in action, and we're really finally getting to see see that real data for the very first time. So to get a sense of what that's like, imagine that you're taking a brand new car out for a spin for the first time. And not only that, you designed and built that car yourself, and it's the only one like it in the world. So you'd be pretty excited about that, and we're pretty jazzed about seeing these SWOT images today.
It's better than winning the Indy 500, that's for sure. All right, so tell us a little bit about what sets SWOT apart. And it's a very special instrument on board called Karen, which we call the heart of the instrument that helps collect all of this data. So Curtis, tell us how Karen works.
All right, so Karen is making measurements that are finer in resolution, wider in coverage, and better in accuracy than anything like it that's come before. So the way it works, the way it makes these measurements is really cool, but it's also a little complicated. So I'm going to try to take you through it one step at a time. Starting maybe with just kind of commenting that these first light images that we're about to see, light is a little bit of a misnomer because SWOT's not using light at all. It's using a radar. And the way you measure water surface heights with radar is I think most people know that a radar instrument is something that sends out a radio wave signal, and by listening for the echoes of that signal to bounce off the target and come back, you can measure the time it takes for those echoes to travel and come back, and that way you can measure distance between the radar and the thing you're observing. So if you put a radar on a satellite with the radar looking down, you can measure the distance between the satellite and the water surface below it. Now these satellites have sophisticated packages of equipment so that we can tell very precisely how high the satellite is, and then with the radar we can tell where the water surface is below it, and that's how we measure how high the water is. So before Karen, that's pretty much how radars operated. But the catch with that is if you're looking straight down trying to measure the water height below the satellite, you can't really tell how high the water is to the left or to the right. And so the previous generation of satellites before Karen were kind of limited in their resolution and coverage. So Karen gets around that by using the distance information from the radar to actually look off to the sides a little bit and form images to either side. And by using that distance from the radar, it can map out swaths of information instead of just getting these 1D profiles. And so by forming these images to one side and the other of the spacecraft, we can get these fine resolution, wide coverage images. Now the catch there is that by using the distance information from the radar to form these images to get wide coverage and resolution, we need to do something else to get the water height now. And so what Karen does is we add a second antenna and use a technique called interferometry, which I'll get to in a moment. But the basic idea you can think of is that if we're collecting images at the same place on the Earth's surface from two different locations, we can get a sense of where those locations on the surface are in three-dimensional space. It's sort of like how with your two eyes you can sense depth because you're getting two images of the same thing from two different places. The way the radar works is a little bit different in that the radar is sensing distance, but it's the same idea that if you observe the same thing from two locations, the two Karen antennas that you can see behind me, one over here and one over here, we can figure out where the surface is in 3D space. It's also equivalent to what surveyors do in terms of triangulating things. We're basically forming an imaginary triangle between the two Karen antennas and the place on the ground that we're trying to observe. And we know where the two Karen antennas are, and if we can measure the lengths of the legs and angles of that triangle, then we can figure out where the point on the surface is and how high it is. So here's where Karen really takes it to the next level, though. If you have these two images and you're trying to measure the surface height very precisely, you still need to get really precise information on what the lengths of the legs of that triangle are. And so Karen uses a technique called interferometry, where it's looking at the phase of the electromagnetic waves coming back from the surface. So if you just heard me say electromagnetic wave, phase, and interferometry, and your head just kind of exploded a little bit, it's okay. We're going to go through that one step at a time. So Karen is a radar, and radars send radio waves out. Radio waves are kind of the same basic thing as the radio waves that your computer or your phone uses for Wi-Fi, or the cell phone signals that you use, or Bluetooth, or AM/FM radio before that. So if you've heard the expression of a broadcast coming to you over the airwaves, it's the same basic thing. I mean, these waves are around us. You use them every day. You can't see them, but they're there. And waves, kind of like the waves you might see at the beach, have crests and troughs, right? They get higher and lower sometimes. And when we sense these waves from the surface from two different locations, the two Karen antennas, sometimes the crests line up with each other, and when you add them up, you get a bigger wave. Sometimes they don't line up with each other, they're misaligned, and the crests of one wave kind of fill in the troughs of the other wave. And then you get some cancellation of the waves. And so the end effect is you get what's called an interference pattern. So that sounds complicated, but the intuitive way to think about it is to think about fringes on a soap bubble. You know, those colored fringes you see on a soap bubble or an oil slick, or maybe the back of a CD or a DVD or something. The same basic thing is happening there because the light that our eyes see is also an electromagnetic wave. And what we're seeing is the light reflecting off of the top surface of the soap bubble and the bottom surface of the soap bubble. And sometimes the light waves are adding up and sometimes they're canceling. So when you see red on the soap bubble, the red light is adding up. The crests of the red light are adding up and the other colors are canceling out. When you see blue, the blue light is adding up and the red light is canceling out. And so these interference patterns that we can observe as the colored fringes on a soap bubble are allowing our eyes to see how thick the soap bubble is, or the variations in the thickness of the soap bubble. Now remember, the soap bubbles are 1,000 times thinner than a human hair, and so these interference patterns let us sense these really minute changes in things. And so Karen is using the same basic ideas, looking at the interference patterns of the radio wave echoes of the radars from the surface, in order to sense these really small changes in the geometry of that imaginary triangle, in order to get really precise measurements of how high the surface is. And so at the end of the day, this interferometric technique, the way that Karen works, is able to measure height variations of just several centimeters or a few inches, and it's doing that from up in space. So I work on this stuff every day, and that basic idea that we're able to see changes like this from 550 miles, 900 kilometers away, that still amazes me.
It is truly amazing. So Karen to me sounds like a hard worker, pulling double duty, and a great listener. And if you're just joining us in right now, we're with JPL engineer Curtis Chen, and we are breaking down SWOT, which stands for Surface Water Ocean Topography. So who's ready to see these amazing images? We have all been waiting to see them. So Curtis, break down these images that have just come down from SWOT and tell us a little bit about what we're seeing.
All right. Let's take a look at some of these images. So behind me, what you're seeing here is one of the images from SWOT showing the changes in the height of the ocean surface. So here you see those two swaths on either side of the spacecraft ground track that I was talking about before. This is the ocean. This is the east coast of the United States over here. And the colors that you're seeing represent the height of the ocean surface. There's a color bar, maybe you can't see it down here, but the red colors here correspond to places where the ocean is about 25 centimeters, or just about 10 inches higher than normal compared to the white areas here. And the white areas here are about 25 centimeters higher than the blue areas down here. And so to get a sense of how small those changes are, if you were on a ship in the ocean, the distances between these red areas and these white areas, that's about 75 miles. That would be way over the horizon, right? So you wouldn't even be able to see that. But you can imagine that even something on the horizon, you'd have a pretty tough time, even with a really powerful set of binoculars or telescope or something, seeing a variation in height of just 10 inches of something that far away. But SWOT is able to see these things from space. And so for comparison, since we were talking about the resolution and the coverage of SWOT, this is a map of what we had before SWOT of the same area, and you can see it's just much lower resolution. This map actually comes from a set of data from 7 different satellites using radars that were only looking straight down. So if we go back to the SWOT image now, what we can see is we just have much better resolution and coverage from just a single satellite overpass. We don't need these 7 satellites in order to see these details here. So SWOT is really just a great advance for this kind of ocean science. But in this next image of Long Island, this is actually my favorite image because this image kind of illustrates how SWOT is making its measurement, and that we're seeing those interference patterns I was talking about before that look like those colored fringes on a soap bubble. But there's also more going on in this image. Let me take it one step at a time. What you're seeing in this image, first of all, this is Long Island with the Pacific Ocean, the Atlantic Ocean on this side over here, and Long Island Sound on this side. This is the island itself. So there are two layers in this image. The brightness, or the grayscale part of the image, represents the reflectivity of the ocean surface, so how much radar energy gets reflected by the surface. And I'll talk more about that in a second. The color layer represents the interference pattern that we're talking about, whether the radio waves coming to our two Karen antennas are adding up or not adding up. And so the colored part is where the magic happens for estimating the heights of the water surfaces. But back to the brightness for a moment. The brightness is something we use to first tell where water is, because over the ocean it's pretty clear water is everywhere, but over land, if what we're trying to do is measure how high water surfaces are, the first thing we need to do is know where the water is in the first place. And so what you can see, some of these areas, for example, these brighter areas are where there's water on the ground. We can see that because they're brighter. Or a little higher in the image, you can see the Conic River. It also appears bright. And so the brightness tells us where the water is. And the color here, whether these bright patches appear red or blue or purple, that's that's the interference pattern that tells us how high those surfaces are. So you can think about the colors almost like contours on a topo map, where the phase of the interference pattern, the measurements we're making with Karen, are that's what allows us to solve for the heights of these features on the surface.
And if you're just joining us, Curtis is breaking down these amazing images that we have gotten down here in the last few weeks from SWOT, which launched last December, and it's tracking over 90% of the water on the Earth's surface. And I really love how we're able to see fresh water on this image as well. And that's what also sets SWOT apart, Curtis.
Yeah, we're able to see fresh water, we're able to see ocean surfaces, but because of that resolution and coverage, we're able to observe things that we just weren't able to observe before. That's just really one of the awesome things about SWOT.
Now, for all of you amazing folks joining us right now, these images don't come down looking like this, do they, Curtis? So what kind of a process do you have to go to so that we can see images like this?
No, when the data first comes down from the spacecraft, it looks like static on an old analog TV. It doesn't look like this. So there's a lot of ground processing involved in order to make images like this and to make other things as well that people can make use of. One of the reasons that the data doesn't look like much when it comes down is that the way that the Karen instrument works, one of the ways it achieves that fine resolution is it's collecting images that are not focused until they come down to the ground. So if you think about the way a camera works, a camera usually has a lens and a sensor of some sort. Like in the old days, it would be film. Now there's an electronic sensor. And the lens is focusing the light onto that sensor. The way Karen works, in order to achieve the resolution that we want, it's almost as if Karen is collecting data like it were a camera without the lens, and then we do the focusing that the lens does on the ground in digital processing. It turns out that's one of the ways that we can get better resolution, because it's, we can't actually build the equivalent of that camera lens big enough in space. So we just do it all on the ground digitally. But after that processing, we can get these beautiful images. We can also produce products that have just easy to understand quantities like latitude, longitude, and height to make the data usable by, hopefully by anyone. The data will be available to the public for download eventually, and we want people to use this data, so we want to make it easy to understand for everyone.
Yeah, that's so great. Easy to understand, available to the general public and the scientists, and put into the hands of decision makers, which is all what SWOT is there to do. And speaking about the data particularly, this is an incredibly large amount of data. Can you just put that into perspective for the folks at home, especially compared to other missions?
Yeah, we were talking about how Karen makes, it gets images, wide coverage and fine resolution, but you do the math on that, that's just a lot of pixels. And so Karen produces a ton of data. It's about 20 terabytes of data a day. For comparison, 1 day of SWOT data is about the equivalent of 5 years worth of data from one of these previous downward-looking radar altimeters. Or another way to think about it is that the data volume coming from the data volume that SWOT produces is is the equivalent of a feature-length movie every 15 seconds or so. So just in the time that we've been talking about this, you probably could have streamed a few movies, and it's just a lot of data to keep up with.
And as much as we love streaming movies, I'm sure all of us do, this is much more productive and better for all of humankind, as you mentioned, which is great. And we can't wait to see more of these images. Now, you've worked on many Mars missions. What is it like to work on an Earth mission now? Has it been rewarding?
It's been great. Working on Mars missions is always a lot of fun because it's just cool to think of your job as being landing something on another planet. But the Earth missions have been rewarding in a whole new way because not only are there really interesting engineering challenges involved, but you get a sense that you're doing something that really matters, that's kind of for the good of everyone, kind of for the good of all humanity. It sounds cheesy to say, but that's one of the ways that I truly think about it. And so it's rewarding on a level that I can feel like I'm addressing some of the important problems of the day.
Oh, so true. And I completely agree with you, Curtis. And I'm so happy that you were able to join us today. Thank you so much.
Thanks for having me, Marina. And also thank you to the whole SWAT team.
It's such a great international group of you, and it's been a privilege to work with you guys. So good luck. And thank you for everything that you do with SWOT as more data images come down. I can't wait to see them and share them with all of you at home. And thank you for all of you for joining us today. And if you want to learn more about SWOT, please follow us at NASA JPL and at NASA Earth. Those were the 2 accounts that were featured on Instagram today. And it's just been a pleasure to be able to join you. And Curtis and I have had so much fun with you. So remember, at NASA Science Earth, your home is our mission. Thank you so much for joining us today, and have a beautiful day. Enjoy the weather.